Hello there, and welcome to the latest Julia Computing webinar, Building Digital Twins with JuliaSim. I'm Misha St. Amand. I'm the head of marketing here at Julia Computing. Now, let me introduce you to everybody else. Today, Dr. Abhijit Dandekar will be showing the advantages and process for building digital twins using JuliaSim. We're excited to have him on board for this. For a little bit of background on him, he holds his PhD from MIT in scientific machine learning. He spearheaded the development of the first SciML model for quarantine diagnosis when COVID-19 hit. And this model has actually been widely used by researchers and policymakers. Since then, he's used Julia's SciML stack for a wide range of epidemiological applications, like early reopening in the US and virtual virus spread. So really great stuff. Dr. Dandekar will be joined today by several members of the JuliaSim development team, Yingbo Ma, Sebastian McLutu-Campanau, Sharon Yalbergi, and Dr. Chris Rakakis, who's the lead developer on JuliaSim, will also be here, and he'll be stopping in the chat and may jump in to answer a few questions. We're excited to have them all here today. As far as questions, if you have any during the presentation, please enter them into the chat question box. We'll be saving all the questions and answering them at the end of the session. So I will allow Dr. Dandekar to take things from here.
Thanks, Misha, for the introduction. Hello, everyone. Welcome to this webinar on building digital twins with JuliaSim. Here is the agenda which we'll follow for today. First, I'll dive into why really Julia is the future of industrial scale scientific computing, following which I'll go a bit deeper into how JuliaSim really enables industries and companies to solve difficult and challenging simulation problems and completely transform their simulation pipeline. And then we'll get to the main topic of this webinar, which is how to build a digital twin of a building. We'll have 2 live coding sessions by Sebastian, Yingbo, and Sharon, which will go a bit deeper into building model, performing simulations, visualizations. Towards the end, we'll show how to build and deploy surrogates. At the end, hopefully we'll have 5 to 10 minutes where we can answer the questions from the chat. So let's get started with the first section on why really Julia for digital twins. So the Julia programming language is already being touted as the next generation technical computing language. It essentially solves the 2-language problem. It's not only very easy to use, but it can also achieve speeds comparable with that of C and C++. It's already the 5th most loved programming language according to the Stack Overflow metric. As the Julia language grows, so is the community and the ecosystem around it. The Julia language is supported by a community who really loves the language and several aspects associated with it. From these graphs, you can see the downloads, YouTube views, the number of packages developed just keep on increasing at a steady pace. I myself transitioned to Julia about 4 to 5 years back and have never looked back since. And now let's come a bit to JuliaSim and what it brings to the table for digital twins. At the heart of Julia computing is JuliaSim. JuliaSim is a next generation cloud-based platform which combines the latest techniques in scientific machine learning with equation-based digital modeling and simulation. Our ML-based techniques accelerate simulations by up to 100 to 500x, completely changing the paradigm of what's possible with computational design. Essentially, JuliaSim offers 3 major things. First, composability. Usually, it's pretty hard to compose code which operates across different domains. But with JuliaSim, you can seamlessly compose codes across different apps. Not only that, we have consistently shown speedups which are up to 100 to 200x, making it fast and scalable. Second, JuliaSim enables need-on-demand distributed and GPU computing. This is especially useful for researchers and people who work in the industry and have to deal with large amounts of data. JuliaSim really makes it seamless to work with big data. And finally, the fusing AI with science part. Scientific machine learning is really a big and a major component of the JuliaSim stack. By combining physics with machine learning, we not only have expressive models, but also models which are interpretable in nature and faster. So essentially, JuliaSim is modernizing the market for technical computing. The core proposition is that products take really long to design. There is a three-step process associated with product design to a laboratory stage to field experiments, making product design really expensive, iterative, and a slow process. Now, JuliaSim, what it offers is that we can really do a lot more on a computer than in the lab or the field. The SciML powered JuliaSim stack cuts down modeling and simulation time by as much as 80%. If you look at the key components of JuliaSim, it can be broken down into 4 to 5 major categories. The first category is that of the modeling tools. Modeling Toolkit and Catalyst are symbolic-based frameworks in Julia, which makes writing down models for several different domains really very easy for engineers and researchers. Second are the model libraries. We have inbuilt custom-made libraries for HVAC, battery, circuit, and these have components which can be used across different domains as well. And finally, the modules. In this, you can see that we have surrogatizers, model optimizers, controls, digital twin generators, and lots more. I'll go a bit more deep into the model optimizer part today. So these three things, modeling tools, libraries, and modules, seamlessly come together to make the JuliaSim apps, such as the FMU Accelerator app and the PID Auto Tuner app. Imagine now you are an HVAC engineer. We can look at what a typical workflow for an HVAC engineer looks like with JuliaSim. First, you write down or build the models using the Julia Modeling Toolkit symbolic library, which really makes it very easy to write down composable models. Second, the model can be accelerated with surrogate trainers. They can then be optimized using JuliaSim's model optimizer. And finally, we have this last part, which is JuliaSim model autocomplete. This relies heavily on the universal differential equations or the UDEs framework, which is the key component of Julia's SciML stack. Imagine you have a model, but there are some missing pieces of information. You replace it with the neural network, train the model, you optimize the neural network, and you can discover the missing pieces of the puzzle. Not only that, the neural network can also be made to give symbolic outputs through the symbolic regression techniques which we have developed in Julia. So now let me go a bit deeper into JuliaSim Model Optimizer. Model Optimizer in JuliaSim essentially helps users relate their models to data by solving inverse problems for parameter estimation. We can also quantify model uncertainty via global sensitivity analysis. In this figure, you can see that there are robust calibration methods such as multi-shooting, etc., which can help us avoid the poor local minima problems encountered in training processes. Let's say you want to quantify the variability in effects observed in clinical trial of patients. JuliaSim enables you to do that. It enables you to do so via generating virtual populations. That is a generation of plausible populations which are sufficiently good fits to all the data sets. And now let us come to demonstration of JuliaSim to build really fast digital twins of buildings. So first, buildings and why do they need precision modeling? A lot of recent studies have shown that a lot of energy, 40% of all the energy is really used by buildings. And precision simulation models are extremely essential for A, optimizing building performance, and B, reducing greenhouse gas emissions. But modeling of buildings is not easy. If you look at the schematic here, you can see that there are several components such as compressor, outdoor coil, there is a reheat coil, cooling coil. To build a model, we have to write separate components for each of these, separate modeling pieces for each of these, and make them composable. Not only that, the underlying dynamics of the whole system can be stiff and non-linear, and all of these combined typically makes the model run times for these systems really high. So we are going to tackle this problem today using JuliaSim, and we are going to build a digital twin. Through this process, we'll show how easy and quick it is to build models and to also accelerate the deployment using surrogates. To give a bit of sense of the physics involved in this process, we have a mass and momentum balance equations in different dimensions, which formed the basis of building this digital twin. Now, after going through this introduction, I'm going to tell a bit more about what essentially we are trying to model here. So we have a 9 by 3 by 3 building, as you can see here, and it's cooled by water circulating at 5 degrees Celsius. The ambient temperature is from meteorological data in Phoenix, Arizona. Through a live coding session, which will follow this slide, we will show how we can model the temperature of different rooms in this building and obtain plots such as the ones shown here. And now I would like to introduce two of my colleagues, Yingbo and Sebastian, who are research engineers in the JuliaSim team, and they will now be assisting with the live code demonstration. So I'm just going to stop sharing my screen, and I invite Yingbo to take it over.
Can you see my screen now?
Yes.
Hi, I'm Yingbo, and I'll present the 3D building model today. The thermal fluid package provides all the necessary components for the building model. And just like the thermal fluid package, Julia Computing also provides libraries for modeling vapor compression, refrigeration cycles, hydraulics, and batteries. So first, let's load all the packages. And the meteorological data of Phoenix, Arizona is also provided within thermal fluid library. So let's load that as well. And we can see that it contains time and temperature. The time is is in the unit of seconds, and the temperature is in Celsius. Because we are only interested in summer cooling of the building, so let's just slice the data starting on July 10th and for a duration of a week. And note that this data is discrete, and for continuous simulation, we have to interpolate them using the cubic spline function. And for thermal fluid modeling, it's much easier to work with Kelvin. So we convert Celsius to Kelvin using the function from degree C. Here we set all the structural parameters of the model. It's saying that in this building, there are 9 floors, 3 rows and 3 columns each floor. So in total of 81 rooms in this building. And we discretize the cooling coils in 10 parts, and then each cooling coil is 10 meters long. And in this section, we set up all the more detailed parameters for the building. But for the sake of time, I wouldn't go into each one of them. But then you can see the documentation for more details. Okay, let me run that. And in here, first we can convert the interpolation object into something that modeling toolkit can understand using the interpolate source component. And the ithnamed micro names this component T ambient. And in here, Q sensibles means a sensible thermal load for the room. For instance, when a person goes into the room, then Q sensible would increase. And for the sake of simplicity, I will just say that no one enters or leaves the room. So it's constant of 20. And these two parameters describes the coolant water. This is saying that the coolant water is always 5 degrees Celsius water. Running with mass flow rate of 0.01 kilograms per second. This sets the fan speed. This is saying that for all the rooms except for room number 5, the fan speed is on unit 1. And at this time for room number 5, it bumps to 2. And in here, we instantiate all the fan models for each room. And because connecting all the rooms walls correctly is very tedious for 3D grid. The thermal fluid package also provides the utility function dense grid building to instantiate all the rooms, walls, and their connections for you automatically. And because there are different types of walls, like interior walls and exterior walls, the walls is returned in a dictionary data structure. And for the modeling, we only care about the actual wall components. So let's just take the values. Yeah, let me run that. So all the equations of this building is the connections between rooms and walls, as well as the connection between the fan and room. So these two connection statements are saying that the output of the fan is the input of the room, and then the output of the room is the input of the fan, just like what you expect physically. And in this section, we connect all the source terms with their respective component, like rooms and fan coils. So let me run this. Because of the sheer size of this model, there are actually over 17K equations in the unsimplified model. Running the structural simplify function will take too long. So in here, it's enough to just run the expand connections function on Turing. The expand connections function expand all the connection statements into concrete equations. And Turing minimizes the model so that it accelerates the simulation time. And finally, in here, we convert the symbolic representation of the system into a ordinary differential equation problem and solve it using the QNDF solver. And because of the sheer size of the model, it's better to turn off the automatic differentiation feature here to minimize the compilation time. It takes about 1 minute to run Turing. Maybe because of the screen sharing, it's a bit slower than that. So let's wait for a bit. And there it finished. And let's just convert it into a numerical problem and solve it using the solver. Yeah, as we can see that it only takes just a little bit over 7 seconds to simulate 7 days worth of real time. And the solver succeeded. And with this, I will hand over to Sebastian for the visualization of the solution.
Hi, I'm Sebastian, and I will now show how the animation that was presented on the slide was created. So, can you see my screen?
Yes.
Okay. So, for this animation, I created this digital twin demo building package, which encapsulates all the code that we need to visualize for the visualization. And I will also be using 2 other packages, Unitful, which is a package that helps us use units in Julia, and Maki, which is a visualization ecosystem for which you can find the docs at docs.maki.org. This line is just to let Maki know that we want to use a more accurate method for the scattering of light, the screen space ambient occlusion. Now, here we have the model initialization and simulation. We had this is the code that was earlier presented. And we have this split such that we can easily access model components for things such as the names of the rooms. For our animation, we need to define our start time and our end time, and of course, how many frames we will have. We also want to define the current simulation time, which will interactively update everything during the animation. With this make figure function, let's now take a closer look to what happens here. Our end result will be, as we've seen, something like this. So we have the building on the left and two other plots on the right. So we have the room temperature and the ambient temperature. We need to first define how are we going to draw the building. For each room, we'll draw a cube, and the positions will be given by the rooms. And for this, we need to take a look at how the simulation was created. So in this sketch, I'm showing how we index the rooms in the simulation. And as we see, we have three indices, I, J, K, such that I goes down and J goes to the right and K goes to the back. But when we do the plotting in Mach-E, our coordinate system is a bit different. So this is why we need to make a coordinate transformation. And this is what these functions do for us. We create the positions as points in 3D space with X, Y, and Z. And as we can see, all of our axes are flipped. So we have to use the minus sign in all cases. And now the room names will be given by room IJK, and the component name will be TR for the room temperature. So as we can see, if we copy this here, we now can inspect that we create the rooms as we wanted. So to translate the room name into a room number, we have this formula. And I also have a helper function that can give us the room number for a given indexing. And as we can see, we have the positions vector. So this one represents our position in the Mach-E space. And if we index it, like, we will get the 3D point that will be corresponding to the room. So we have for 1, 1, 2, we have 3 to 9 as expected from here, and the room number will be 28. If we go, for example, with 211, this will be the room just below. And as expected, the all room temperature names at position 2 is just 211, which corresponds to our indexing. Now, as we've seen, we select two rooms to cut so that we can see the walls between them better. And these are the 111 and 121 rooms. And the walls are indexed such that we give the room numbers between room 1 and room 10, and then room 10 and room 19. Now we have to go through the indexing so that we can get the positions of these rooms. Now we have to do the mapping of the temperature to colors. So we need to define a temperature range that will correspond to the color range, which is what this code here does. And we can see that we can use easily the unitful package to easily convert between Kelvin and Celsius, as we've learned earlier that our simulation uses Kelvin. But for visualization, it's easier to show it in Celsius, or we can just change this to F and we go in Fahrenheit, and the same for seconds and hours. With this code now, we can also interactively link the temperature in the rooms to an interactive variable that depends on the visualization time. So we can use the solution indexing, and for more information about this, we can look at the docs in solution handling in differential equations documentation at the DFQ SciML.ai. And we can see here that we have this indices keyword that also works with symbols, not just with numbers. So we request the solution for this component, which means what is the room temperature in our digital building, digital twin building. And now if we want to see in Celsius, what does this mean? It will be the time given, so the current visualization time. And if we change this, we see here that it also changes, but we need something interactive. So this is an interactive variable. So let's create an interactive variable, which now takes the interpolated visualization time and outputs our current temperature. And if we now take the visualization time and change it to, let's say, 10, A is 25 point something. And now if we go to, we can see that our variable automatically changed its value. So let's do one more because, okay, so you see it automatically changes without needing to call anything on A. And this is the basis of how our animation will function. Now we set up the temperature for the cutout rooms, for the rest of the rooms, and for the walls. For actually drawing each of the rooms, we will use rectangles, which will have the dimensions of 0.9, so that we can use 0.1 for the walls. And also we'll add a ground below, so it will be another rectangle just so that our building doesn't float in space. Now we can go back to how our figure will look like in the end. And we have to create our layout. For this, we can also consult the Mackie documentation. So in the tutorials, there is the layout tutorial, which will tell us more about how layouting works in Mackie. Now, we have these grid layouts, which index into the figure, so we can intuitively understand what happens. So we have GA, which will be the first, and if we go as in a matrix with 2, we'll have the grid layout for the right hand side of the figure. Now we have to define the axis for the room temperature, which will be in GB, the first position, and right under it will have the ambient temperature. So we have 2 here. And for the building, we'll index in GA. And this uses an LSIN, which, as we can find in the docs, is used for 3D plots. The axis is used for 2D plots. And here we have some keywords for setting up the lighting so that our building looks nice in the animation. And we hide the axis because we don't need it. For the actual components of the figure, we will use mesh scatter to create the building, and this is presented here in the docs. And we also use the ground will be defined by a mesh. Here, as we can see, we give the axis as the first argument, the positions, and then the marker will be the rectangle, and the color will be given by the interactive room temperature. Now we can also move on to showing the room temperatures here by converting the temperature from Kelvin to Celsius. And you also, when we request the time in the solution, we have to go from hours to seconds because the time is in seconds, but we have hours on the axis. The same goes for the ambient temperature, and we also draw some vertical lines to mark the position of the current time. We also have this setup camera function, which positions the camera in this angle that's presented in the figure by accessing the eye position of the camera, where the camera is looking at, and how much do we want to zoom in, and what's called the up vector. So that's that direction for the camera. Other than that, we also, for the animation, we can zoom in during the animation on the building, or on the building, just showing the rooms at the top. And for this, we define the end position that we want to arrive, and just to make that time dependent. So the camera will move during the animation. So let's set up the camera, and now we'll display the figure, and this is the figure. And we can pan around it. And now our, just a second. Our building is now ready to be animated, and we can use the animate function for this. And as we can see, at this specific point in time, this room starts to cool down because of the, as my colleague mentioned earlier, the fan coils, it goes from 1 to 2. We can now also change this to true. So we set up again the figure, the camera, and display it. And now when we animate it, it will move just like we expected. And with this, I will let Raj continue explaining about the surrogates.
Thanks, Sebastian. I'm just going to share my screen. I hope everyone can see my screen. So now I'll dive a bit into surrogate trainers offered by JuliaSim. So surrogates in JuliaSim essentially bring together physics and machine learning to lead to simulations which are really fast. And we are going to show one such application of surrogates to the building digital twin model, which we have shown up till now. To do this, we'll use a technique called continuous time echo state networks. Just to give a bit of an introduction of CTESN. So continuous time echo state networks can be used for generating surrogates of non-linear and stiff ODEs. So a classic way to really create surrogates for stiff systems is to just eliminate the stiffness using problem-specific transformations. But CTESN technique is generally applicable without any user-specific interventions. So echo state networks as a technique are a reservoir computing framework which projects signals from higher dimensional spaces called a reservoir. The CTESN, or the continuous state time echo state network, it allows for an underlying adaptive process to really avoid gradient issues while training. There are 3 layers which are important here. There is an input layer, there is a reservoir layer, and there is an output layer. R is the state of the reservoir at any time t. And so essentially the CTESN can be used as an underlying core for training surrogates, which will be now explained by my colleague Sharan in the next section. So he'll also be going a bit into a live coding part. And towards the end, we'll show that the speed ups which are obtained using surrogates is really of a very high magnitude, which enables faster computations and simulations. So now I'm going to stop sharing my screen, and Sharon, you can take over from this point.
Thank you, Raj. Let me just quickly share my screen. I hope you can see my screen.
Yeah.
Yeah. So hey everyone, I hope you're having a nice day. And I'm Sharon, a research engineer in the JuliaSim team. And before I go deep into the digital twin generation code, let me first introduce you to our documentation. So to get to our documentation, if you just go to help.juliahub.com, and then if you can go to the surrogates tab, you'll find a bunch of tutorials and detailed API and manual documentations. And let me kind of preface this by saying that there are two ways we can train any given machine learning model to match a physical system, which we call a digital twin. The first is to have a physical description of the model, such as an FMU using a functional mockup interface specification or a modeling toolkit model. So we support both, but in today's case, we'll be using the modeling toolkit model generated, explained by Yingbo. And the other way is to directly have data which you can train on, which we won't be covering today, but that's also possible. So in order to start this off, the first thing which you need to do when you have an FMU or a modeling toolkit system is data generation. So we provide a dedicated module to enable this, and it's called data generation.jl. So what it enables the user to do is specify the sampling spaces. So which parameter space are they interested in? What kind of initial conditions are they interested in? And what kind of control inputs do they expect to see? So if they can define the space, we enable fast parallelized data generation. And this is enabled through JuliaHub's parallelization features. And we also provide a neat simulator to enable this easily within the JuliaSim ecosystem. And this also gives the output in a format which is easily ingested into the rest of our pipeline. So the second part is pre-processing the generated data. And we have a dedicated module for that too. And this enables simple pre-processing like normalizing, and also enables much more complex domain-specific pre-processing, which the user might want to code up on their own. And you can even chain these multiple pre-processing steps how you see fit. And the next part after you pre-process the data is to actually train the digital twin. And we have a dedicated surrogatization module for that. And what this module enables is that it gives you like these pre-built models, like the CTSNs, which Raj just described, and also other stuff like extreme learning machines, CTSNs, etc. So in today's case, we'll be using the continuous time echo state network. And this module enables you to directly use that model without having to worry about its implementation details. So next part after you train a model is to be able to visualize it and to see where it performs well, which parameter range it performs well, and where it kind of lacks, and maybe we want to like generate more data in that region and so on. So we have a dedicated module for that. And as you can see in this, we have a dashboard which presents us with what kind of speed up we are getting with this digital twin, and it also gives you the error metrics in different subspaces of the parameter space, right? And this will enable you to explore and see where your model is lacking, where it's doing great, which parameters are troublesome in which subspaces or sub-ranges. And you can find more details on it here. And all of this pipeline, all of the data required for this dashboard is already generated in the previous steps or the previous modules. So the next part is logging. Logging enables you to kind of keep track of the performance and how reproducible your code is. And we have a bunch of macros for that. And this will make sure that you're making the best use of your resources. Yeah, so let us head back into JuliaHub now. And to start off with, our starting point is obviously the model, which Yingbo described earlier, which is using the Arizona data and for over a week's time span. And we are essentially running the same model. And then I have a bunch of build and compile step, as Yingbo described earlier. For the sake of time, I've already generated the data of that model in a parallelized way using JuliaHub. And if you go to the data here, like the generated data, you can see that it's essentially what we are interested in for the surrogate is just the temperatures of two rooms, room 2 and 3 in this case. And it's recorded across the timestamp of starting from 0 all the way to 1 week amount of time. And we'll be using this as a starting point today. And let me just quickly introduce you to the code. So we start off with like importing all the relevant packages and importing all the data which we have already generated. Keep in mind that this is running on JuliaHub and it's all running on the cloud. And I'm just using this on a browser. Once we are able to import the data, we also define our T-span of our simulation, which is 1 week, as Yingbo mentioned earlier. And we also mentioned the lower bound and upper bound of the parameter space we are interested to train over. Once we do this, we also pre-process the data. And we also fit a cubic spline to get a continuous time approximation of it. And now we start with actually training the LPCTSN. LPCTSN is linear projection continuous time echo state network. So what it essentially is a linear projection on the reservoir, which the continuous time echo state has. So it starts off by actually defining the reservoir system, reservoir ODE system, and then solves the reservoir ODE system. Then it generates the bunch of W outs, which Raj had explained. And these W outs are later used to fit a radial basis function. What the radial basis function essentially does here is it interpolates in between the different W outs. So there's basically one W out for every parameter sample. And RBF helps you to interpolate between parameters. So during test, it's you might not be using the parameters you trained on, right? And the radial basis function helps you interpolate the right W out. We also define a predict function here. Now let us quickly visualize how we have actually trained. And it's pretty good, actually. If you look at the error bars, they're pretty minimal and very close to 0. There's some aberrations in between, but this can be improved with more data, probably more pre-processing, and maybe tuning the model to have a larger reservoir. And there are many tricks in the trade. So you can see that even if you zoom in closely, you can see that it fits pretty well to the simulation, to the original system being simulated using traditional numerical solvers. And it's all doing that much faster. And it's actually doing it like 11,000x faster. So I can quickly show you the time it takes to actually do one prediction. So here I'm computing the time, and you can see that it takes around 6 milliseconds. This is down from 7 seconds, which Yingbo had shown that it takes to solve using traditional numerical solvers. And even that was pretty great, 7 seconds, but we are down to 6 milliseconds after we train a surrogate on the actual states or observables we are interested in. Yeah, that's it from my end. I'll hand it over back to Raj to continue the presentation. Thank you.
Thanks, Sharon. So I hope everyone can see my screen. So Sharon just demonstrated the speed up which we have from surrogates, and it's really awesome to see the predictions match the data pretty well as having such a huge improvement in the performance. And with that, we come to the end of the demonstration which we had from our side. I hope through this demonstration, we provided an overview of how JuliaSim can really be used to make virtual representations of physical systems, how modeling toolkit can be used to create composable subsystems and link them together in one piece of code. And when that is linked with differential equations.jl, which really has the most extensive and powerful solvers out there, it leads to a very powerful modeling stack. This, along with surrogates, which have scientific machine learning at the core of it, leads to a whole digital twin ecosystem in JuliaSim, which is powerful and it's really, really fast and easy to use. So with this, we probably have around 10 minutes for question and answers. I saw that Chris has answered a lot of questions on a chat. So if anyone has any more questions, please feel free to ask.
We'll give it just a second if those of you who have questions haven't typed them in yet.
I think someone is raising their hand. Rick is raising the hand.
Oh, yeah. Let's see. Oh, I just saw a question on the chat which says that I see catalyst.jl. Are there more process engineering libraries? So there is a library called catalyst.jl, and that along with modeling toolkit are the predominant symbolic computation frameworks. But if Yingbo or anyone else knows any other libraries, please feel free to add.
Yeah, well, so there are some partnerships that Julia Computing is doing for the development of process engineering libraries. I would say that, if you are interested in some of these commercial libraries, just get in touch with sales at juliacomputing.com and we can tell you a bit more about that. Some things that are involved are the ability to generate new refrigerants and some of their properties and different mixture properties, and then use that to see how different buildings would operate, or different HVAC systems, how efficient they would be in different scenarios with these different properties. So if that's the kind of thing that you're looking for, please get in touch. And there are also a few other libraries in development, and we'll have different webinars that are based on these other pieces as well.
Okay, should we give a second to allow Rick to ask his question?
Yeah, thank you. So the question I had is in regard to the displays that were being shown for evaluating the performance of the reservoir computing model. And as I understood it, the emphasis was on getting insights into the efficiency and sort of explain some of the value or the contribution of different parameters. But not so hypothetically in an environment even today, if one were to take this approach, someone, you might have colleagues who are suspicious about machine learning or how well it's able to reproduce results. So I'm just curious, is there some part of the analysis or the displays which would help lead to things like, for example, being able to explain how it's working, or to show sort of the explainability, I guess, of the models, or perhaps how it can generalize beyond, say, the test models. So again, the sort of the usual buzzwords we hear with these kind of topics, but it'd be useful to have some kind of tools that would help to use those points to communicate to a broader audience in some environments.
Yeah, so I can maybe answer that initially, and then Sharon or Chris can add. So one thing definitely, one type of technique which can help the interpretability is the symbolic regression, which we do along with the SciML stack. So what we have seen when we apply these scientific machine learning methods is that along with expressivity, so along with capturing the details of the missing physics, what we are now enabled to do is answer questions like, what are the symbolic terms which the optimized neural network really represents? Is it a cubic term? Is it a quadratic term? And that really gives more interpretability. In fact, in an uncertainty quantification sense, we have even reached stages where we can ask questions like, how many percentage of the times does the neural network recover this particular term? And how many percentage of times, let's say, it recovers a wrong term? So by combining these ML frameworks with more techniques of symbolic regression, or let's say objects such as Bayesian neural ODEs, we can attach an interpretability along with the expressivity. And that's what, in my opinion, makes SciML or scientific machine learning very powerful. So my experience was in epidemiology in my PhD research, and the models which we developed during the COVID time, they were not just ML frameworks, but they had a lot of physical interpretation attached to it. In fact, they were used as diagnostic tools. So it's a step towards mitigating the apprehension towards just the buzzwords of ML and just those being thrown around everywhere to fit stuff.
Yeah, and I would like to add that, basically what we're trying to show is that the right visualization tools might be the answer to how you can explain the interpretability and the accuracy of these different machine learning based, simulators, right? So, if you have the original simulator, when you build a digital twin, you can always ask, how close is this to the original model, right? Because you can run the original model, you can run the machine learning model, see how far apart they are. But the thing that really happens with the visualization is then you can kind of see, well, for what parameters are the error the highest? What is the maximum error? You can kind of, you can't get a sense of what every single parameter will be like, but you get a good sense of the parameter space, and you can use this to really find out, where is the digital twin more trustworthy and where is it less trustworthy? And I think that with that kind of sense, you can then know how to use it effectively. And I think that's the real key that we're trying to get out of this visualization.
I know Chris is still typing a few answers.
Yeah, and I'll take one of these live. Someone asked about, is it possible to do these surrogates on FEM models? We actually have been doing this with some of our customers, and this has been working well. And so definitely you can do this on finite element models, because anything that works with the surrogates data generation process, which includes ODE problems, is able to be, or it includes ODE problems and FMUs. These can be used as inputs. So for example, an ODE problem that is generated from GridApp or generated from Ferrite, these finite element libraries, or if you have a finite element simulation that is able to export to the FMU interface, these can all be used as inputs for the circuit generator.
Okay, I'm gonna let Chris wrap up the questions he's typing, and I just want to thank everyone on the call: Raj, Yingbo, Sebastian, Sharon, Chris, thank you all for joining us today and all these demos and things you've shown us around digital twins and JuliaSim. And for those of you who joined us, thank you so much. Really appreciate you being here and really love the great set of questions. As promised, we'll send up a follow-up email that will include a link so you can review the recording of the webinar. And of course, if you have additional questions, you can always reach out to us at sales@juliacomputing.com. If you enjoyed the webinar, please keep an eye out for future webinars. We're going to be talking about JuliaSim's Model Optimizer in November, as well as an exploration of different JuliaHub workflows to speed your Julia development. To find out more about this, you can sign up for our monthly newsletters at juliacomputing.com. Thank you everyone for attending, and we appreciate you being here. Thanks everyone.